This sequence of videos is going to go through friction and the different types of friction. In previous videos, we've used friction a little bit and we've known properties like what direction it goes, and we've tried to be careful about the notation we use to differentiate or distinguish between the different types like static versus kinetic. Now we're going to move more into the quantitative side. What do you need to do to really use friction in calculations? So we are going to clarify the different types of friction. There's really three different ones that we talk about. There's really two that we primarily use. For each of these, we're going to define the direction and magnitude. And obviously the magnitude is going to be really important for doing calculations. We'll do a little bit preparing for actually doing some calculations, though again, this video will be focused more on the conceptual work and setting things up, and we will actually define what our friction model is. So we're actually going to start with that, even though the book ends with that, since I think this is helpful to try to see what's going on overall. And again, a lot of the basics that we're using right now, like how we use notation for friction, has been defined in the past. So really what we're focused on here is moving into problem solving. So first, let's talk about the friction model. So the friction model is a simplification. This is a major simplification in that we'll talk next slide, what is actually happening at the microscopic and even the macroscopic level. And so what's really happening is very complicated. We don't want to calculate that. So instead, we're just going to make this nice simplification. So in our simplification, there are three types of friction. And we say that friction, no matter what type it is parallel to the surface. And we always are talking about a surface since friction is the interaction between an object, like this box, and a surface. The surface might be vertical, it might be at an angle, but there must be a surface. Now, it might be the surface of another object, like one box sitting on another box, but it's always a surface. So friction is always parallel. That's really important and a big part of the model. So then we have three types of friction, and the first is static friction. So this is where the biggest simplification is coming in a way, in that we just say that static friction acts as needed to prevent motion. So this is a little tricky to think about. If you understand what's happening microscopically, this might make more sense, but we actually are saying that this can have any magnitude up to a certain value. So we're going to calculate this. Like, this is going to be the equation we use for static friction, but it's really important to recognize that that is a maximum value. And so static friction doesn't have a fixed value. You have to calculate what it is based on other things that's happening in the scenario, unless you know that static friction is at its maximum, if, for instance, you're calculating when it's about to slip. And we'll talk more about this in a little bit. But this is a big deal. We're saying that this is a force that somehow seems to know what it needs to be. And that isn't really what's happening. Forces aren't sentient. However, mathematically, that is how the model works. So the second type of friction is kinetic friction, and this opposes the motion, and in this case we have a fixed value. So once it's sliding, we know what the force of friction is, and this is the kinetic friction force. So that one in a way is simpler, but you have to recognize when that's the scenario you're in. The third type of friction is going to be the one that we talk about fairly rarely in here, which is rolling friction. And rolling friction is kind of a hybrid case between kinetic and static. And so this equation looks just like the kinetic one. And so really, in a way, you can think about it as a variation on kinetic friction. And we won't usually use that in here. It's so small that we usually just consider it negligible. Now, there's this picture here that I think is really, really helpful for understanding friction. But what we're going to do is actually come back to this friction at the end of this series of videos after we've studied a little more what's happening with static and kinetic friction, and hopefully then we can interpret it. So I don't think we're ready to do this quite yet. Before we delve into our specific three types of friction that go into our model, I'd like to really talk about what's happening at a microscopic level. And this is still a little bit from analogy. If you've studied chemistry or material science at all, this might make sense to you, and you might understand this at a deeper level than what I'm presenting here. So the first thing to think about is that all surfaces are rough. For some of them, that's macroscopically, if you think about sandpaper, and for others, that's microscopically. So even the surface of glass, which feels very smooth to your hand, is still going to be rough on a microscopic level. So what that means is when you put two surfaces together, they stick and interlock. So that's kind of what this picture shows, is the interlocking. Now there's two aspects to this. One is that there are very few points that are actually in contact. That much of the surface has a little bit of a gap between them, but then some points are actually in contact. The other thing you can see is that because both surfaces are jagged, there are going to be points like this here where the jaggedness of one piece can kind of stick. It can go up into the other surface. And that's one thing that prevents them from sliding. So the sticking is a slightly different effect. The interlocking is kind of the up of this lower surface going into the up of the upper surface. But you also have molecular bonds that form. And again, this is physics class and not chemistry class. So there are obviously different types of bonds, and these are, for instance, hydrogen-hydrogen bonds, or bonds due to polarization. So they're not as strong as the bonds that, for instance, hold a water molecule together, but there's still an attraction at an atomic or a molecular level. And when you get things very, very, very close together, this happens. There's an interesting phenomenon called cold welding, where if you polish two pieces of metal in a way molecularly smooth, and you make sure that there's no oxidation on them, and you put those two pieces of metal together, they actually fuse, and you can't possibly pull them apart. And it has to do with this phenomena, that molecules, as long as you get them close enough, or atoms, depending on the type of material, will actually stick together. So when you have this rough surface, points are actually close enough together that they stick, and other places are actually interlocking. So something to think about is that the more normal force you have, i.e. the harder you push those two surfaces together, you're going to have more of this interlocking and more of this sticking. And the analogy that I like to use is Velcro or Lego. So again, we're kind of talking about two surfaces where it's nice and jagged, and then there's another surface that's also jagged, and that if we pushed harder, they would move up together. And so as we push harder and harder and harder, they go up and merge together more. And so now we have larger areas that are in contact, or at least more areas that are in contact, and it's going to be harder for them to slide horizontally since the jaggediness are more interlocking. So you can kind of think about this like Legos, if you've ever played with Legos, that when you push two Legos together lightly, it's very easy to pry them apart. But once they're really stuck together, it's much harder. Similarly with Velcro, that Velcro is actually made up, it's also called hook and loop closure. Velcro is actually the brand name. You have lots of kind of loops on one side, and this is the part that feels smooth, kind of like fabric. And then the other side is made up of a bunch of little hooks, and that's usually the part that feels rough to your hand. So when you push them together, you actually are latching some of those hooks into the loops. And then it's not really possible for it to slide because they're latched together. But if you don't push very hard, not many of them hook together. So those are just analogies, but I think it helps think about what's happening with friction, that really this is about a molecular scale interaction. And so this is also where we come back to our model. What we're going to talk about for static, kinetic, and rolling friction is not at all about molecules. So what we are talking about is a simplification, it's a model, it's something that typically works in experiments, but we're not actually worrying about the details. So that's the whole point of doing physics modeling. We're simplifying a scenario so that we can calculate it, but our model needs to still agree with experimental results.